Hey everybody, it's Thursday, October 1st. We made it to October. As you can see there on the aim, today we are going to focus on using everything that we've said so far about graphing to solve some problems. So yesterday, we talked about a lot of the concepts involved in graphing, solved a problem, and then looked at a worksheet with questions on it. As I said here in the beginning, and something I'm going to continue saying for the entire year, the only way that you can learn physics is to do physics. And so that's what we're going to focus on today. The best way that you can possibly get a feel for how these graphing concepts are applied to solving problems is to solve problems and apply these graphing concepts. That's the ball game here. So what we're going to do today is take a look at worksheets full of great graphing problems. So if you looked at the post on Google Classroom, you would have seen a series of attachments. Those attachments are the worksheets the problems that we're going to solve today are on. And so what I'd like you to do first is go back to Google Classroom and locate the AP Physics graphical representations of motion, velocity versus time graphs, speed versus time graphs worksheet. It is a long name. If you can't see the whole name because it got cut off, it's the worksheet with these 6 velocity versus time graphs shown at the top. And we're actually going to work on this worksheet almost in reverse order. So I'd like you to scroll all the way to the bottom, because the first problem I'd like you to look at is B1 SCT30. This code, SCT, we are going to be seeing a lot this year because these are called student contention tasks. They actually do this on the AP test too. They will say student A says this, student B says this. What part of what this kid said is right? What part of what this kid said is wrong? And then your job is going to be to resolve their disagreement. So we're going to slowly work up to this in stages as we get to the slightly more complicated ones that are on the AP test. So in this problem, B1 SCT30, it says the graphs below show the velocity of 2 objects during the same time interval. And it says 3 students are discussing the displacements of these objects for this interval. And we have our 3 students, Amos, Badu, and Candy. And what I want you to do, as it says in the bottom, is figure out which student you agree with, if you agree with any of them, or say none of them if you agree with none of them, and then explain why. Again, the students are discussing the displacements of these objects for this interval. Because this particular problem is not that involved, I'd like you to take, let's call it 3 minutes to pause this video. And when you hit play, we'll go over the answer. So during this 3-minute time period, and just look at it on the time on your computer or your phone, I want you to work on this problem. And after 3 minutes, I want you to wrap it up. And when you hit play, we'll discuss the answer. Okay, so these 3 students make these 3 claims, and your job was to figure out who says the correct answer with the correct reasoning. Amos says, I think object 2 will have the greater displacement because it gets to a higher speed faster than object 1. Sounds pretty good. No, Badu says no, object 1 will have the greater displacement because it travels for a longer time than object 2. That's a pretty good point also. Candy says, I agree with Amos, but for a different reason. Object 2 has the larger displacement because the area under the graph is greater. So when you see kids in these problems mentioning like real concepts that we're discussing, you definitely want to interrogate that for a minute. So Candy is talking about the area under the graph. This is a velocity versus time graph. What does the area under the curve for a velocity versus time graph represent? What do you know? It represents the displacement. So that seems like a pretty good claim. Now, obviously, what we want to do is figure out if that's actually correct. Yesterday, when we were looking at area under the curve, we said a good way that you can estimate area under the curve is by counting the boxes underneath the graph. And so rather than actually calculating the area under the curve, we can just go ahead and count the boxes. That looks like a half a box. And that also looks like a half a box. So we can call this whole section here, this whole triangle, one box. Again, this is an estimate, but that seems like a pretty good estimate. That's one box. That's one box. And this is also one box here. It's important to realize that what we have going on here is like almost an alternate interior kind of Z, right? And so that means that the size of this box is going to be the size of this box. And so this whole thing is 1. And that means this whole thing is 1. So we have 1, 2, 3, 4, 5 boxes for graph 1. And for graph 2, we have 1, 2, 3, 4, 5, 6 boxes. And that's the point here. Candy is correct. The area under the curve represents the displacement, and the displacement is greater because the area is greater. That's it. And the reason why area under the curve works very well is illustrated by Amos and Badu's answers. Because what they are trying to do, if you think about it, what they are trying to do is they are trying to look at the equation V equals d over t and solve it for distance. And notice, Amos is saying, well, object 2 goes farther because the speed is larger. Well, the speed is larger, but the speed is only part of it, right? If you go 100 miles per hour and I only go 10 miles per hour, but you go 100 miles per hour for 1 minute and I go 10 miles per hour for 5 hours, I go farther. It's not just about the velocity. It's about the velocity and the time. And so notice, Badu gets to that point exactly because he says, well, wait a second. The time is larger for object 1. So object 1 goes farther. And the area under the curve is the way to go about this question because it captures both of those things simultaneously. Because area is the length times the width, it captures both the speed and the time issue together. And that ultimately is why Candy's right, because she mentions an explanation that captures both of those things. Any explanation about graphing where the person is mentioning slope or area under the curve is usually the one. All right, so your answer should look a little something like this. The displacements of the objects can be found simply by finding the area under the curve. Since the area under the curve is larger for object 2 has a larger displacement. That's it. Get straight to the point. Tell me the concept. Area under the curve is the displacement. And then you apply the concept to the question. The rest of it is really just logic. If area under the curve is displacement and the area is bigger, then the displacement is bigger. That's the only logical conclusion one can draw from that information. Take a second to write that down if you didn't already. And I'd like to take one little note about that because that's going to come up again and again and again. And our note for this question looks like this. Notice this pertains to that question B1 SCT 30. The area under the curve for a velocity versus time graph represents the displacement of the object. To quickly compare areas under the curve for graphs with a grid space, we can count the number of boxes bound between the line on the graph and the x-axis. To be clear, the AP test asks you to do this. So you should be prepared to do that. Take a second to pause this video to write that down, and when you hit play, take a look at another problem. Okay, so let's move on. The next problem I want you to do is on that same sheet, but it's actually the first problem. I want to be clear, we are actually going to skip this middle problem, WWT 19. And the reason we're going to skip it is because it's actually another kind of graphing problem that we are going to get to either tomorrow or Monday. And so we're going to skip WWT 19, and the next problem we're going to look at is B1 CRT 09. B1 CRT 09 says velocity versus time graphs or speed versus time graphs. Velocity versus time graphs for 6 toy cars that are traveling straight along a hallway are shown. All graphs have the same time and velocity scales. And so they show you these 6 velocity versus time graphs. And the task here is for you to draw the speed versus time graphs. So I know that because this scan is terrible, the grid spaces got washed out sort of for C and F, but just do your best to sketch the curve, and that's really all we could ask for here, and then explain your reasoning. The key thing I want to focus you on as you start this is, what is speed? What is velocity? How are they related? And how are they different? Take a second to pause this video. I think 4 or 5 minutes to work on this and write the explanation will be good enough. What is speed? What is velocity? How are they different? How are they related? Pause this video, take 5 minutes to complete this one, and when you hit play. Okay, so the question I asked you before you should have hit pause for this video was, what is speed? What is velocity? How are they different? How are they related? Speed and velocity both measure how many meters someone travels in a second. And the real difference between them is that one is a vector while the other is a scalar. That means that because velocity is a vector, it carries directional information, while speed is a scalar, so it does not. So velocity has directional information, speed doesn't. And the real question you have to ask yourself is, how does velocity show you information about the direction? And it shows you information about the direction from the sign. And so the key idea here is that while velocity can be negative, speed can't be negative. And that's the real difference between them. So if you look at A is showing you a negative constant velocity, and it's -1 unit. Because speed can't be negative, the speed versus time graph should just show a positive speed. Speed, because it's a scalar, can never be negative. So it's going to be equal in magnitude and just with no direction. And that's really the answer for all of these questions. For B, the velocity starts positive and stays positive at 1.5 and then decreases to 0 by the 1, 2, 3, 4, 5th time marking. And so the speed graph should just look exactly the same. Speed, at least instantaneously speaking, meaning at any particular instant, is the magnitude of the velocity. notice C is the mirror image of B. So since the velocity starts negative, -1.5, the speed should start positive at 1.5. By the third mark, the velocity gets to be just under 1, negative, and so the speed should just be just under 1 and positive, and then it gets to 0 by the fifth time mark, so this graph should look exactly the same. Wherever the velocity is negative, the speed is the same amount, it's just positive. For D, because the velocity is positive the whole time, at 1.5 units, the speed should be positive the whole time at 1.5 units. For E, same concept, wherever the velocity is negative, the speed has to be positive. So the velocity gets to 0 at the 2.5 mark, and wherever it's negative, so notice it starts at -1, the speed should start at +1. And so rather than just being a straight line, it should just look like a V, like this. And then for F, it's the same graph. The idea here is that the speed is the scalar version of velocity. And so since speed is a scalar and velocity is a vector, we can think of speed as being the magnitude or the absolute value of the velocity. All negative velocities in this case should be reported as positive speeds. That's the idea. Notice that second little note I wrote there at the bottom, there is no negative speed. Speed, because it's a scalar, can't show direction. And so it can't be negative, it can only be positive. Take a second to write that down. And when you're finished, let's write down this note. For instantaneous values, the speed is the magnitude of the velocity. Essentially, what we mean here when we say for instantaneous values is like if you remember back to when we first started talking about average speed and average velocity, we were getting average velocity numbers that were smaller than the average speed. Average speed captures really, and average velocity captures really like the overall trip. That's why we refer to them as average speed and average velocity. When we're talking about instantaneous velocity or instantaneous speed, we're really talking about the velocity at one particular instant, instead of talking about the average over the whole trip. So for that reason, when we want to refer to the velocity or the speed at one particular instant in time, we call it the instantaneous speed or the instantaneous velocity. Suggest you pause the video here and write those last two things that we just said down. And when you hit play, we'll move on to some more problems. Okay, so now that we've finished those two problems on that sheet, we are done with that sheet. Remember, the middle problem on that sheet, this one here, I don't want to show the answer, I only have the key open, but this middle problem, B1 WWT19, we are going to save for later once we discuss that topic. And so if you go back to the Google Classroom page, what you will see is that there was a second sheet posted. The title is Graphical Representations of Motion, Velocity versus Time Graphs of Children, Kinematic Quantities worksheet. And what you'll see when you look at that worksheet is there are 3 questions on that sheet. And what I want to do is I actually want to do this one in reverse order as well. And the reason why I want to start with B1 QRT 56 is because this question is sort of similar in style to the last question we just looked about. They are not asking you to draw graphs again, but I'd like to do this one first. So go ahead and open that up. It says here, again, this is B1 QRT 56, this is one of those qualitative translations where you take sort of a number representation like a graph and you translate it into words. It says position versus time graphs for boats traveling along a narrow channel are shown below. The scales on both axes are the same for all these graphs. In each graph, a point is marked with a dot, and I hope that's obvious looking at each of those graphs. And there's a series of questions, 6 questions underneath, that I want to take a look at. I actually want to go over all of these, but I'm going to tell you to do them 2 at a time. Because if you look, notice A and B are asking about position, C and D are asking about velocity, and then E and F are asking about acceleration. So for this first group of questions, I'd like you to take a look at A and B. A and B are asking you for which graphs, which of these cases, if any, is the position 0 at the indicated point, and then for B, for which cases, if any, is the position negative at the indicated point. This is pretty straightforward, and the explanation, I think, should be pretty straightforward as well. So I'd like you to take maybe 2 minutes to answer A and B only. And when you hit play, we'll go over A and B. Okay, so for this question, it says, for which of these cases is the position at 0 at the indicated point? This question, I think, here is pretty simple. They're asking you when the position is zero at the indicated point. So the question is, for a position versus time graph, how do you determine the position? And that's the easiest question of them all, because you just read it off the graph. So the answer here is point C. Since this is a position versus time graph, the value of the position is determined by the y-axis. You read it off the graph. That's it. That's really all there is to this one. It's pretty straightforward. They're asking you when the position is 0. It's 0 there because the graph says that's where the position is 0. It doesn't get any simpler than that. So that one's pretty straightforward. Pretty easy. Okay. Now let's take a look at B. B, similarly, is pretty easy. It says, for which of these cases is the position negative at the indicated point? Again, you read it off the graphs. So for graph A, the position is negative. For graph B, the position is negative. For graph D, the position is negative. For graph F, the position is negative. And for graph H, the position is negative. The y-axis variable is position. Position is negative whenever the labeled point is below, oh my God, the x-axis. That's the idea. When they're asking you information about position and the graph is a graph of position versus time, you just read it off the graph. That's about as easy as it gets. Okay, so that's it for A and B. Now, as you can see here, we started easy and now we're going a little more difficult. The next 2 questions, C and D, are asking you about the velocity. Remember, this is a position versus time graph. I'd like you to take a minute to look at these 2 questions. And I know I just said a minute, that's a figure of speech. To get the answer and to explain your reasoning, let's say, I'd like you to take 3 or 4 minutes. Pause this video, take a look at C and D. For which of these cases, if any, is the velocity 0 at the indicated point? And then for D, is it negative at any of the indicated points? Explain it. And when you hit play, we'll go over it. Before you do that, though, I just want to say very quickly, you do not need, if there are multiple answers, like graphs A, B, C, D, E, whatever, you do not need to explain every graph individually. The point of these explain your reasoning questions is there is an overarching concept. So you just give the overarching concept, and that's it. Take 3 or 4 minutes, pause this video, and when you hit play, we'll go over it. Okay, so for C and D, they're asking you about the velocity. And as I said before I asked you to pause, the main thing you need to think about here is that this is a position versus time graph. And so the real point of this question, or these questions, I should say, is how do you determine information about the velocity from a position versus time graph? And the answer is the slope of a position versus time graph represents the velocity. So all you have to do is look at the slope. Now, we have a bit of a problem. And the problem we have here is that the graphs, every graph besides A, are curved. So if they're curved, then how do we figure out anything about the slope? And if you remember in the video the other day, what I was talking about was using the idea of the tangent line. And so the idea here is that to determine the value of the slope at any particular point for a graph that is curved, you sketch in the tangent line and then you take a look at it. So let me go ahead and show you this for all the graphs. Sorry. So to show you this for all the graphs, I'm going to sketch in red the tangent line. Now, obviously, it's kind of, that's not red, it's blue. Let me do it in red. It'll stand out a little more. The tangent line for A doesn't really make sense because it's a straight line, but we could sketch it in there if you want. It would look like that, right? For B, remember, the tangent line is just a line that touches the curve at one point, so it would look something like that. For C, it would look something like that, maybe a little more horizontal, though. For D, it's going to look something like that. Again, a sketch here is really all we care about. For E, it's going to look something like that. For F, it's going to look something like that. For G, a little something like that. For H, like that. And for I, like that. And the question, and I'm going to keep these so we can revisit them later. The question for C says, for which of these cases is the velocity 0 at any indicated point? So now that we have all the tangent lines drawn, the question is, which of those tangent lines has a slope which is equal to 0? The slope of a line is 0 when the line is horizontal. And the only one that has a horizontal tangent line is graph E. Notice when it's a parabolic shape like this, whether it's an upside down parabola or a regular parabola, at the bottom, if it's a regular parabola, or at the top, when it's an upside down parabola, the tangent line will always have a 0 slope. And so what we can say here for our answer is graph E. It was E, right? Yeah. Graph E, and we'll say here the slope of a line tangent to the curve for a position versus time graph is the velocity. When the slope of the tangent line is 0, the velocity at that point is 0, since the slope represents the velocity. That's the idea here. I think that's pretty straightforward. Once you get the hang of this, I think you'll find that that's pretty easy. The slope of the tangent line gives you the velocity, so you sketch in your tangent lines and you look at what's happening. Since the slope of the tangent line is 0 for graph E, the velocity is 0 for graph E at the labeled point. It's the same kind of answer for D. For D, they're asking which of the cases, if any, is the velocity negative. So all we have to do is look at these tangent lines and see which of the tangent lines drawn have a negative slope. And the key thing to remember here, I think, is that if a line has a positive slope, it looks like this. And if it has a negative slope, it looks like that. So graphs with a negative slope of the tangent line are D, F, G, and I. D, F, G, and I. And again, we can say here the slope of the tangent line for a position versus time graph represents the velocity. Since the slopes of the tangent lines are negative, and the slope represents velocity, the velocities are negative at those points. And that's the idea. When a graph is curved, you don't need to worry. If they're talking about a particular point, you just sketch the tangent line or a line tangent to the curve. And then all you have to do is examine the slope of the tangent line. To be clear, for this course, you are never actually going to have to calculate the slope of a tangent line. You are just going to have to draw it, sketch it, and figure out if it's positive or negative. So that's not too bad. And that's it for C and D. To wrap this one up, I just want you to take a look at E and F. Now, E and F are fairly complicated. E, not so much. F is pretty complicated. I want you to think about if an object has, as E is talking about, or sorry, as F is talking about, a negative acceleration, what does that actually mean? If the acceleration is negative, what is that going to do to the object? So take 4 or 5 minutes to take a look at E and F. Write your answer. You could pause the video here, and when you hit play, we'll go over them. Okay, so for part E, this one's pretty simple because it says for which of these cases, if any, is the acceleration 0 at the indicated point? And to some degree, this is a game of which one of these is not like the other. Because this is a position versus time graph. And position versus time graphs have a slope which shows you the rate of change of position. Or in other words, the velocity. And when the velocity is constant, that's when the acceleration is 0. So to figure out which graph is showing you a constant 0 acceleration, you are looking for a constant slope. Because if the slope is constant, the velocity is constant, and that means the acceleration is 0. Now, the way that you tell the slope of a graph is constant is if the line is straight. If the line is curved, that means the slope is changing. And only one of these graphs has a constant slope. And that's graph A. Graph A is the only graph here with a constant slope. So that's it. We can say here for this one graph A, the slope of a position versus time graph is the velocity. When an object has a 0 acceleration, the velocity is constant, meaning the slope of a position versus time graph should be constant. and that means the line is straight. And so just to fully tie this in here, we can say since the slope in graph A is constant, the velocity for graph A is constant. So the acceleration is 0. And that's it. That one's pretty straightforward. The slope tells you the velocity. When the slope is constant, the velocity is constant. When the velocity is constant, the acceleration is 0. Pretty straightforward. Now for F is asking you when the acceleration is negative. And this one is kind of tricky. And so I want to go back to the graphs here and think about the slopes of the tangent line. Again, first of all, it's definitely not A here, so we can just get rid of that. While I think it's instructive to draw the tangent line at the point, you also want to do it slightly before and slightly after, because that will give you a good sense of what's happening. So notice here, I'm drawing the slope of the tangent line at the point and then slightly before and slightly after. And so our goal here is going to be to figure out what does a negative acceleration do to an object? And the answer is, I hope you've internalized from what we were talking about the other day, the answer is, well, that depends on the object's initial velocity. If the initial velocity is positive and the slope, if the initial velocity is positive and the acceleration is negative, the object's going to slow down. But if the initial velocity is negative and the acceleration is negative, the object is going to speed up. So here's the deal. If an object has a negative acceleration and it starts with a positive velocity, the velocity is going to get less positive or more negative. And if the object starts with a negative initial velocity and it has a negative acceleration, the velocity is going to get more negative. So let's look at B. B starts off with the slope of the tangent line that's basically 0. Then it's tilting more upward, and you can tell that it's tilting more upward if you just extend that line. Notice here the slope is tilted more. The slope gets even greater here as the graph curves up. So the velocity starts positive, and it gets more positive. That acceleration is positive. That's not what we want. Let's move on to C. C shows the velocity start positive. Then it gets a little less positive. And then notice it gets even a little less positive. If an object started out with a positive initial velocity and it's slowing down, that means the acceleration is negative. So there we go. C is one of our answers. Let's look at D. D shows the initial velocity start positive. Notice if we extend that line, the graph is curving away from it. Notice the slope of the tangent line is negative, then a little less negative, then a little less negative, and really at the end, the slope of the tangent line is 0 when the curve bottoms out, so to speak. So the velocity was negative, but it's getting less negative. And if an object has a velocity, an initial velocity that's negative, and it's slowing down, that means the acceleration is positive. So that is not our answer. So far, we only have C. E is an easy one because the velocity starts positive goes to 0 and then goes negative. And the only way a velocity can start positive, then go to 0, and then go negative is if the acceleration is negative. So E is one of our answers. Looking at F, the initial slope of the tangent line is basically 0. This object really starts from rest. Then the slope of the tangent line gets negative, then more negative, and then even more negative. And the only way an object starting from rest can have an increasing negative velocity is if the acceleration is negative. So F is an answer choice as well. So notice so far, our negative acceleration has been demonstrated in a lot of ways. We had a positive initial velocity for an object that stopped. You see this curve where the slopes are decreasing. We had a negative acceleration with an object that had a positive initial velocity, stopped, and then turned around. And we have a negative acceleration for an object that was at rest and then sped up in the negative direction. For G, the initial velocity starts here negative, then it gets less negative. Notice if we extend that line down further, it's starting to curve away from it, less negative until the slope is eventually 0. So if an object starts off with an initial velocity that's negative and slows down and stops, it can only do that because of a positive acceleration. G is wrong. For H, this one's a little confusing because the position starts negative. I'm going to say this, I want to make sure everybody gets it. Even though the position starts negative, the object's initial velocity is positive. You can tell that by the slope. Do not be confused by that. Position is where the object is on the axis. The velocity is the direction it's going. So it just means the object started over here to the left of the origin, but moved to the right, where the left direction is negative x and the right direction is positive x. So this velocity was positive, then decreased until the velocity eventually becomes 0. And if an object has a positive initial velocity and slows down, it's because the acceleration is negative. That makes the answer H. And then for I, initial velocity is negative, less negative, 0. The only way that's possible is if the initial velocity is positive. So our answers here are C, E, F, and H. Chef. C, E, F, and H. And what we can say here is the slope of a position versus time graph represents velocity. Since acceleration is the rate of change of velocity, when the acceleration is negative, velocity must have a negative rate of change, or in other words, it must get more negative or less positive. That one, in my opinion, is for sure the most complicated one on this sheet. But you have to think, what is the relationship between the sign of the initial velocity and the acceleration? What would a certain kind of acceleration do to a initial velocity of one sign, and what would it do to an initial velocity of another sign? That's the way to think about these problems. Take a second to pause this video and write that down, and then we're going to take a few notes about this because this is very important. Okay, let's write a few things down about that because that's a really important kind of graph. There are a couple things I want to say here. The first thing we want to say, which I hope was obvious to everybody, even if it's not, on a position versus time graph, the position can be determined simply by reading the value off of the y-axis of the graph. That's it. It doesn't get any simpler than that. You just literally read it off the graph. The velocity at any instant or point, particularly its sign, And the reason I'm saying that is because you don't actually have to calculate the slope of a tangent line, because really you need like a computer to draw it for you to get it to be exactly right. So you just need to figure out its sign. The velocity at any instant or point, particularly its sign, can be determined by looking at the slope of a line that is tangent to the curve at that point. If you remember that pen trick that I was talking about the other day, moving your pen around and seeing how it changes, I think that really is a smart way to go about doing that. Of course, you can draw them like I just did right now, but it'll save you a lot of time to make use of that pen trick. And lastly, and this part was pretty important, I think, since acceleration is the rate of change of the velocity of the object, the sign of the acceleration can be determined by examining how the velocity, which is the slope of the tangent line, changes before or after a point. Take a second to pause this video here and write that down, because there's one more thing I want to say about that acceleration bit. Note, a negative acceleration turns a positive velocity less positive and a negative velocity more negative. And of course, I'm talking about a negative acceleration here because that's what was in the question. But if the question had a positive velocity, all these would just be opposite, right? If it was a positive acceleration, the positive velocity would get more positive and the negative velocity would get less negative. And remember, this goes back to those two rules that we were talking about when we first started talking about acceleration. When the velocity and the acceleration are the same sign, the object speeds up. And when the velocity and the acceleration are the opposite signs, the object slows down. Take a second to pause this video, write that down, and when you hit play, we'll take a look at another problem here, and then we'll wrap this up for the day. Okay, so in this problem, next one we're going to look at, B1 WWT48, this code, WWT48, it's called a what's wrong task. Your job is to figure out what's wrong, if anything, and explain why. So it says here, the graphs show the velocity versus time for two boats traveling along a straight, narrow channel. The scales on both axes are the same for the two graphs. In each graph, a point is marked with a dot. A student who's asked to compare the accelerations at the marked points on the two graphs states, I think that the boat in graph B has the larger acceleration because the boat in graph A is at rest at the marked point and its acceleration is 0. So your job, as it says here, is to answer the following question. What, if anything, is wrong with this student's contention? If something is wrong, identify it and explain how to correct it. If it's correct, explain why. I'd like you to take 3 or 4 minutes, pause this video, answer this question. If something's wrong, say what it is and say why it's wrong. And if something's right, tell us why it's right. When you hit play, we'll go over it. Okay, so in this problem, the kid says, I think that the boat in graph B has a larger acceleration because the boat in graph A is at rest at the marked point and its acceleration is 0. So the kid makes 2 claims. Let's evaluate those claims. The first thing they say is the boat in graph A is at rest. Well, that's true. The velocity at that indicated point is 0. It's exactly on the x-axis. But then they say the acceleration is 0. And that's not true. The main idea here, this question gets at a misconception that kids always have, and that's why we're talking about it so much. Physics students always seem to think that if an object's velocity is 0, that means its acceleration also has to be 0. Now, some of you, I would imagine, might be thinking that same thing, but that is not true. And one of the reasons why this annoys me a little bit is because I know you guys know this already. Because when we were in regular physics, when we were talking about either an object thrown thrown straight up in the air or a projectile fired at an angle, we said when the thing reaches its maximum height, it stops. But the fact that it stops does not mean gravity stops accelerating it. Gravity slows it down on the way up and then speeds it up on the way down, but the acceleration acts the whole time. So the acceleration is not determined by the velocity. The velocity is determined by the acceleration. So the answer here is all about the slope. The acceleration for both boats is given by the slope of the graph, which is equal for both graphs during the interval shown. The slopes are the same. You can see just looking at it, the lines are parallel. At the point indicated, graph A shows an object at rest, but it still has a non-zero acceleration. That's the idea. And we can tell that the accelerations are the same because the y-axis variable increases by 1 unit in 2 time units, and that's the same thing that happens over here. The rise is 1 when the run is 2. And that's really it for that one. If you want to write that down, go ahead and pause here. But now that we finished that, we really only have one more question to look at on the sheet, and we'll just do this question and call it a day. This question is the top one on this page, QRT 36, velocity time graphs of children. And this question says the velocity time graph shown represents the motion of 2 children, Ariel and Byron, who are moving along a narrow, straight hallway. Do either of the children ever change direction, is what they're asking you in part A. If so, at what time or times does the change in direction occur? B is asking you if the 2 kids ever have the same velocity. And C is asking you if the 2 kids ever have the same acceleration. I want you to go ahead and answer all of these, explaining your reasoning. Remember, it's a velocity versus time graph. And I want you to pause this video and take, let's say, 7-8 minutes to work on A, B, and C. And when you're finished, hit play, and we'll go over them. Okay, so the first question, part A, asked, do either of the children ever change direction? If so, at what time or times does this change in direction occur? Explain your reasoning. The most important thing to remember about this one is that the graph is a graph of velocity versus time. And an object's direction of travel is determined by the sign of the velocity. So the answer here is yes. When an object's velocity changes from positive to negative, its direction changes. Ariel's velocity changes at 5 seconds. Notice you can see Ariel's line crosses the x-axis at 5 seconds. And Byron's at 6.5 seconds, indicating a change in direction because their velocities go from negative, meaning they're traveling to the left, to positive, meaning now they're traveling to the right. Okay, part B asked, do the children ever have the same velocity? If so, at what time or times does this occur? Explain your reasoning. I think this one's pretty easy too. The graph, remember, is a graph of velocity versus time. So yes, the 2 children have the same velocity at 2 seconds and at 9 seconds. Velocity is given by the y-axis variable, and the lines overlap or intersect twice, indicating the same y-axis value at 2 seconds here and at 9 seconds here. So when the lines intersect, it means whatever variable is graphed on the y-axis, those things are the same. And then for C, C says, do the 2 children ever have the same acceleration? If so, at what time or times does that happen? And this one is a bit tricky. So I would suggest we take a look at this more closely. So the first thing you have to ask yourself is, this is a graph of velocity versus time. So how do you get information about the object's acceleration? You get information about acceleration by looking at the slope of a velocity versus time graph. Now, Ariel's acceleration is constant because Ariel's line is straight. But Byron has a curved line, and so you have to look at the slope of the tangent line. And so notice, to start, it should be fairly obvious the slope of the tangent line for Byron's curve is significantly smaller than the slope for Ariel's line. As time goes on, though, the slope of that tangent line increases until right in the middle, the slope of the tangent line, really at about 6 seconds there, the slope of the tangent line is the same as the slope for Ariel's line, which we can tell because they're parallel. So again, let me show that one more time, because that was pretty terrible. Slope of the tangent line shows you the acceleration. And at 6 seconds, you can see there, and maybe if you tilt your head, that's when, if you draw a line tangent to the curve, the slope is the same. So the easiest way to do this, remember, is to take your pen, which I can't really show that on the screen, so I'm just going to draw a line, is you want to take your pen and hold it at various points along the curve. And so if we look at the slope of the tangent line there, we see that it's still less. But as we move it along and we hold it at about 6 seconds, you can see that if you shifted your pen from here down to there, you would notice your pen will become parallel to the other line at about 6 seconds. And that's how you know the slopes are the same. And so the answer here is yes. The accelerations will be the same when the slope of Ariel's line is the same as the tangent line to Byron's V versus T curve. And the tangent line and the slope of Ariel's line are the same, or they have the same slope at time t equals 6 seconds. It's a little tricky when the lines, or I should say, it's a little tricky when there are curves instead of just a straight line, but it's important to remember whenever you have a curve, all you have to do is think about the slope of a line that would be drawn tangent to the curve at that point. Let's just take a few quick notes about that problem and wrap it up for the day. This is a velocity versus time graph, so let's remember a few key things. First, since the sign of the velocity shows the direction of travel, a velocity versus time graph shows an object changing direction when the line on the graph crosses the x-axis. That is crucial. Number two, velocity versus time graphs show objects having the same velocity when the lines on the graph intersect. Also important, but I feel like that was pretty obvious. And number three, since the slope of a velocity versus time graph is the acceleration, the V versus T graph shows objects having the same acceleration when the slopes, or slope of the tangent line, are the same. I suggest you write this down, so take a second to pause this video and write that down, and when you hit play, I want to ask you one more quick question before we go. Weird question. If Byron started at the origin of the coordinate system, does he end up on the left or right side of the origin? If Byron started at the origin of the coordinate system, does he end up on the left or right side of the origin? Take a second to think about that. We'll go over it here in a minute. All right, if you still need more time to think about this, go ahead and pause the video. And when you hit play, then you'll hear me going over it. The question asked, does Byron end up to the left or right side of the origin if he starts at the origin? And the important thing to realize is essentially what that's asking you is about the displacement, whether the displacement is positive or negative. And so the real question is, how do you figure that out? Well, this is a velocity versus time graph. What you need to look at is the area under the curve. And so the area under the curve, remember, is the area bound between the x-axis and the line on the graph. And for Byron, ignoring Ariel's line for a second, that's all this area here until 6.5 seconds. And then after 6.5 seconds, this area here. And so really what this question is asking you to compare is the positive displacement to the negative displacement. And so here, all you have to do is count the boxes. We've got 1, 2, 3. Let's call that between the two of these 4.5, just an estimate. But over here, we have 1, 2, 3, 4, 5. We can call these 6. That's basically 7. That's basically 8. So it's definitely bigger on the negative sign than it is on the positive side. And if the negative displacement is bigger than the positive displacement, then that means the total displacement is negative. And if the total displacement is negative, that means he ends up left of the origin, because he started out going to the left, and though he did come back right a little bit, he wasn't able to make it back to the origin because his positive displacement was less than his negative displacement. All right, everybody, that's it for today. Tomorrow, it seems like at the pace we're going, will be the last day for graphing. We are going to take a little bit at the beginning to focus on reviewing some graphing calculations. I'll give you the opportunity to practice that one more time. And then we will take a look at a new kind of graphing problem, which is probably one of the harder things of the year. And then we will move on. Have a good one, everybody.